Mars is the most explored planet in the solar system. From the first images, he shows strange signs, channels, unusual formations, signs that seemed artificial. In 1976, the Viking 1 probe photographed a mountain shaped like a face. The face of Mars became a symbol of possible built structures. Years later, high-resolution images showed that it was just a shadow play, but the doubt remained. Several meteorites found on Earth came from Mars. Some of them contained structures that looked like microscopic fossils. Over the past 30 years, rovers and probes have discovered dry riverbeds, minerals that only form with water, and organic molecules. Mars once had lakes, rivers, and perhaps oceans. In 2025, new evidence was released. Satellite images, rover data, and laboratory analyses have rekindled the question: was Mars ever inhabited? In recent years, the Perseverance mission has focused on exploring Jezero Crater, where there is strong evidence of an ancient lake. Drill samples have revealed sedimentary rocks containing organic compounds. These compounds contain carbon, hydrogen, and oxygen, and are integrated into clay minerals, formed in the presence of water. Analysis shows that these materials did not come from meteorites or volcanic activity. The possibility of biological origin has come to be considered serious. Most importantly, these molecules were found in rock layers dating back 3.5 billion years, precisely when Mars was wetter and possibly habitable. In 2024, the mission began preparing sample tubes to be sealed and left at strategic locations. These tubes will be retrieved by future missions that will bring them back to Earth for direct analysis in laboratories. Images captured by the rover's cameras showed rounded patterns in rocks that resemble stromatolites, formations known on Earth to be generated by colonies of microorganisms. These patterns were observed in areas where there was accumulation of aquatic sediments. It is not definitive proof, but the morphological pattern is highly suggestive. In parallel, the Trace Gas Orbiter once again detected methane in different points of the Martian atmosphere. This gas is unstable and degrades over time, which indicates an active source releasing methane today. It could be an underground chemical reaction, but it could also be a form of microbial life. In the Utopia Planitia Plain, the Chinese rover Zhurong found layers of soil with different levels of hydration. Using ground-penetrating radar, it identified structures that resemble channels or cavities carved by water. Minerals altered by the presence of liquids were also detected. Some of these deposits are more recent than previously thought, with ages estimated at up to 1 billion years. This extends the window of Martian habitability well beyond the wetter era, and reinforces the idea that Mars may have had habitable niches for long periods. In 2025, Italian researchers published new data from the Mars Express mission indicating that there is more than one subterranean saltwater lake at the south pole of Mars. The hypothesis was reinforced by radar measurements showing reflections consistent with liquid bodies beneath layers of ice. The presence of salts, such as perchlorate, would prevent the water from freezing, even at extremely low temperatures. These reservoirs could harbor microbial life, similar to that found in subglacial lakes on Earth, such as those in Antarctica. Future missions plan to drill into the region to collect direct samples. Meanwhile, the European ExoMars mission, postponed due to the war in Ukraine, has resumed with a new schedule. The goal is to drill up to 2 meters deep, where organic compounds may be preserved from radiation. The Rosalind Franklin rover is equipped with spectrometers capable of identifying amino acids and complex molecular structures. Between 2021 and 2024, orbital observations also showed seasonal changes in areas of the Martian soil, with the appearance of dark streaks called recurrent slope lineae. These patterns suggest temporary brine flows. Although they are not necessarily liquid water flowing on the surface, these structures continue to be monitored as possible indicators of recent hydrological activity. In addition, changes in the concentration of radon and hydrogen have been detected in certain regions, which may indicate underground interaction between minerals and liquids. In short, the volume of data increased dramatically between 2020 and 2025. The pattern that repeats itself is clear. Organic compounds, geological structures linked to water, active gas emissions, and indirect signs of processes that, on Earth, would be linked to the presence of life. None of these discoveries are isolated. They accumulate and paint an increasingly consistent picture that Mars had the conditions to support microbial life in the past, and perhaps still does, in a hidden form, beneath the surface. In the late 19th century, Italian astronomer Giovanni Schiaparelli observed Mars through a telescope and reported long, straight lines on the surface. He called them canali, which means channels in Italian. The term was mistranslated as canals in English, suggesting artificial structures built by some civilization. The idea spread quickly. American astronomer Percival Lowell spent years studying these supposed canals. In his drawings, Mars appeared covered by a vast network of straight, interconnected lines, as if engineered. He believed a Martian civilization built the canals to transport water from the poles to dry areas. These interpretations dominated public imagination for decades, even without scientific confirmation. At the time, there were no real images of Mars, only visual observations and speculation. With advancing technology, NASA's Mariner 4 flew by Mars in 1965. It was the first spacecraft to send actual images of the Martian surface. The photos revealed a cold, dry planet filled with craters, nothing like an inhabited world. Expectations dropped, but doubt persisted. In 1976, the United States launched twin probes, Viking 1 and Viking 2. Their goal was to land, photograph, and analyze Martian soil for signs of life. It was the first direct attempt to detect biological activity on another planet. Each lander performed 3 biological experiments. One of them, the labeled release LR test, had a positive result. When the Martian soil was moistened with nutrient solutions marked with carbon-14, a gas was released, possibly indicating microbial metabolism. But the other 2 experiments did not detect organic molecules. This contradiction left the results inconclusive. Scientists decided not to confirm life based on one isolated signal. Beyond the experiments, Viking 1 captured a famous image, the face on Mars, a rocky formation in the Cydonia region resembling a human face staring at the sky. The photo, taken in low resolution, looked symmetric due to shadows and angles. In the 2000s, the Mars Global Surveyor rephotographed the same area in high resolution. It revealed the face as an ordinary hill, no artificial structure. Still, another kind of clue appeared. Several meteorites found on Earth were identified as fragments from Mars, ejected by ancient impacts. One of them, ALH 84001, gained attention in 1996. Inside, NASA researchers found microscopic structures that looked like fossilized bacteria. The announcement was cautious, but triggered worldwide debate. Experts argued for years whether the structures were true fossils or natural mineral formations. There is still no definitive answer. These early clues, historical observations, inconclusive tests, and debated findings, didn't prove that Mars once had life. But they opened the way for new, more advanced missions to look for clearer answers. Today, Mars is dry, cold, and has an extremely thin atmosphere. But geological evidence shows it wasn't always this way. Satellite images, probe data, and Martian rock studies indicate that billions of years ago, Mars had rivers, lakes, glaciers, and possibly entire oceans. Ancient drainage channels, deltas, and dry riverbeds are visible in several regions, such as Valles Marineris, Eberswalde, and Gale Crater. The Curiosity rover, which landed in Gale Crater in 2012, found sedimentary layers, clay minerals, and calcium sulfate veins, all formed in the presence of water. The sediments indicate that a lake existed there for millions of years, fed by rivers and rainfall. Other rovers like Opportunity and Spirit also found strong signs of chemical alteration caused by liquid water. Rocks showed hematite and sulfates, minerals typically formed in watery environments. The Perseverance mission, which landed in 2021 in Jezero Crater, targeted an ancient delta. This kind of structure only forms with sustained water flow. Rocks in the delta revealed layered sediments with grain size variations, a classic sign of river deposition. Beyond geology, spectrometers detected clays and hydrated salts across the surface. These minerals are direct indicators of long-term water presence. Climate models using topography and atmospheric data suggest that Mars once had a thicker, CO2-rich atmosphere, capable of maintaining temperatures above water's freezing point. It may also have had an active magnetic field, which would protect the atmosphere from solar wind. Studies show that between 3.5 and 4 billion years ago, Mars experienced a period called the Noachian Era, marked by intense geological activity, meteorite impacts, and abundant liquid water. It's believed that Mars gradually lost its atmosphere after its magnetic field weakened. Without protection, the solar wind began stripping away atmospheric particles, lowering pressure and causing water to evaporate or freeze. The MAVEN mission, in orbit since 2014, confirmed this theory by measuring how the Sun still removes particles from Mars's upper atmosphere today. Mars in the past wasn't just wetter, it was potentially habitable, with stable liquid water, a milder climate, and physical conditions similar to early Earth. These features make Mars the leading candidate in the search for life beyond our planet. In recent years, the search for life on Mars has moved far beyond distant speculation. Based on solid data, scientists started using Earth's extreme environments as analogs. In the Atacama Desert, bacteria live hidden inside rocks, protected from intense radiation, a setting strikingly similar to parts of Mars. In Antarctica, microorganisms have been found in lakes trapped beneath kilometers of ice, proving that life can survive under brutal conditions for millennia. Meanwhile, labs here on Earth have recreated Martian chemistry in controlled experiments. Substances collected by rovers were exposed to extreme cold, CO2, and ultraviolet radiation. The result? Some organic molecules lasted much longer than expected, especially when shielded by minerals like clay and sulfates, both common on Mars. This supports the idea that ancient biosignatures could be preserved underground. Analysis tools have also become more precise. Modern spectrometers detected variations in carbon isotopes from Martian samples, variations similar to those produced by biological processes on Earth. Nothing is confirmed yet, but the pattern appears across multiple locations and instruments, making the evidence harder to dismiss. One 2025 finding drew major attention: formations that resemble fossilized biofilms, thin layers of mineralized microorganisms. Seen in rocks through advanced microscopy, they show a structure and organization nearly identical to Earth's microbial mats. Their origin is still debated, but their location, in places where liquid water once flowed, raises eyebrows. New climate models add more weight. They show that Mars went through warming cycles, shifting from frozen states to brief, warmer periods. During those times, liquid water may have resurfaced near geothermal hotspots like Elysium Planitia. These sites are now top targets for upcoming missions, since warmth and water together create ideal conditions for underground life. Speaking of missions, 2025 introduced a bold idea: the Subsurface Life Explorer. It's designed to drill up to 10 meters deep in biologically promising areas, using AI to analyze samples in real time. The goal is no longer just to ask if Mars was habitable. It's to search for signs of life at the source. Private companies are stepping in too. Miniaturized instruments are being developed to detect biological signals with high sensitivity. The plan is to launch a fleet of microprobes across various regions of Mars, forming a decentralized and simultaneous exploration network. The shift is clear. We're no longer just looking for Earth-like environments. The mission now is to hunt for biosignatures, chemical compounds and structures that, on Earth, only appear in the presence of life. The focus is sharper, the tools are better, and the answers might be closer than ever. Don't blink. The moment we discover life on Mars could be just around the corner. Subscribe for more discoveries that could change everything.